Hi there! Power shunt stroke Zener diodes have their virtues. Unlike a switching power supply, they don't have any switching noise, can be made very accurate, have a fast response time, and are inherently short-circuit proof. And naturally, there's always a downside. They're mostly inefficient and power zeners can be expensive. Yet with the addition of a power transistor, they can be made for less. Let's now look at my setup. Firstly, we have on the left hand side a amp meter which is set to 10 amps, and that's measuring the input to my power shunt stroke Zener Diode Regulator. And then on the right hand side we have a voltmeter which is measuring the output to this regulator, which should be a nominal 5 volts for this particular setup. And then we move over to the MOSFET, the IRF 540, dissipating into a heatsink which is fan assisted. Then we move down to my ancient breadboard with a red LED in the middle of it set there. Then let's move over to the right hand side, and that is a car bulb with 2 filaments within, a 21 watt and a 5 watt, and both elements are parallel to create the approximate resistance of a power resistor R1. And then finally moving down to a second car bulb used as a load. As a reference, I've used the band gap of a red LED to drive the IRF 540N, taking a nominal 12 volts DC to approximately 5 volts DC at 1 amp output. Other output voltages are achievable by using different coloured LEDs or stacking them in series, or you could simply use a small wattage Zener diode. I don't have many power resistors, so I've used car tail bulbs instead. Whilst perfectly acceptable, these bulb filaments have a non-linear behaviour. Their resistance is low when cold and higher when hot. That's a positive temperature coefficient, isn't it? In fact, it's an S-shaped VI curve. It's also worth adding that my breadboard setup is barely adequate for the currents involved. Let's now start at the beginning, dynamically testing this simple regulator. This is under no load condition, and as you can see the bulb is quite bright, and I'm covering that for the camera. The input current is 1.63 amps, and as there's no load, all of that current minus about 1/4 amp for the fan is going through the IRF 540 MOSFET. This is producing an output voltage of 5.34 volts DC. I've now placed across the output a 5 watt filament, and I'm just covering that bulb because of its brilliance, and it's drawing 1/4 amp. Add that 1/4 amp to the fan's 1/4 amp and look at the input current of 1.65. You've got to take away 1/2 amp from that, which is 1.1 amps approximately, and that is what the power MOSFET is passing. The output voltage has dropped very slightly to 5.17 volts DC. I've swapped out the 5 watt filament load for the alternate 21 watt. It's loading the output to the tune of about 1 amp, and I've uncovered it so we can see how dimly it is glowing. The input current of 1.63 represents a very slight drop from the 5 watt filament load, and slightly oddly the output voltage has actually gone up very slightly to 5.33 volts DC. If we take the output current of 1 amp plus the quarter an amp for the fan, take that away from 1.633, we end up with the power MOSFET only passing about 0.4 of an amp, and that is quite cool. This is now driving the shunt regulator at absolute maximum load, and what I'm doing is using both the 5-watt filament and the 21-watt filament as a load, and because it's bright I need to cover it. You can see that the input current has lifted ever so slightly and the output volts DC has dropped to 5.05 volts DC. The combined current of both output filaments represents 1.25 amps, and if we add the fan current of 0.25 of an amp and take that away from 1.66 input amps, you end up with the power MOSFET only passing about 160 milliamps. To prove my statement that this is inherently short-circuit proof, the shunt regulator, I've reconnected the 21-watt output load filament, and you can see it glowing slightly, and I'm going to short-circuit the output a number of times and let's see what happens. Under a short-circuit condition, R1, which is constructed out of a 5-watt and 21-watt element in parallel, is up at maximum brilliance because it's getting 12 volts across it, and the input current, as you can see, jumps up to just over 2 amps. There is a small residual voltage on the output, and that is due to the voltage drop across these rather thin wires at these currents.